and welcome to this class. I am Ngubani Kirsten, and I'm here to take you on the subject chemistry. The theme of our class today is chemistry and environment, and I'll be taking you on the topic hydrogen, part 1. At the end of this lesson, you should be able to write the electronic configuration of hydrogen, identify the isotopes of hydrogen, and write the electronic configuration. You should also be able to explain the unique position of hydrogen in the periodic table. Then you should be able to state the physical and chemical properties of hydrogen. Now, the name hydrogen was coined from two words, hydro and genes. They're actually Greek words, meaning water and generator or producer. It was discovered in 1776 by Henry Cavendish. He produced it by treating iron with dilute sulfuric acid. Hydrogen is also known as the most common element, as it makes up 75% of the entire universe. Although it does not occur on Earth in its pure form, but it is the major element in stars and gas planets such as Jupiter and Saturn. Now, what is hydrogen? Hydrogen is a chemical element, okay? It has a symbol H, and it has an atomic number of 1. This means that it contains just one proton in its nucleus. It also has just one electron in its outermost and only shell. So in drawing the atom hydrogen, we can have something like this, okay? This is the shell, and here is the nucleus with just one proton and one electron. We'll be looking at the electronic configuration of hydrogen. The electronic configuration of hydrogen is 1s superscript 1. This is because hydrogen has only one electron in its outermost shell. Looking at the picture here, we'll see that the one which is written as a superscript represents the number of electrons that hydrogen possesses. So it has just one electron, so that is why we have 1 as a superscript. The one here, written before the S, signifies the energy level. So this electron is found in the first energy level or first subshell of the hydrogen atom. That is actually the only subshell that the hydrogen atom has. So the electron is found in this first subshell, and that is why we have 1s. The S here represents the type of orbital or subshell. So this is the electronic configuration of hydrogen. Now, for hydrogen to fill its energy level or obtain what we call the duplet structure, which would actually be 1s superscript 2, it only needs one more electron. Now, duplet structure, atoms of elements usually undergo chemical combinations in order to obtain what we call duplet or octet structures. Elements are always looking for a way to become stable or non-reactive, just as what we call the noble gases. They do this by possessing either 8 electrons in their outermost shell or just 2 electrons in their outermost shell. Those that achieve a stable electronic configuration with just 2 electrons in their outermost shell are known as duplet structures, while those elements that obtain stability with 8 electrons in their outermost shell are known as octet structures. Now, most elements obtain this octet structure by having 8 electrons in their outermost shell. It's just a few elements that obtain a duplet structure, such as hydrogen and lithium. And hydrogen does this when it accepts just one more electron to its subshell, okay, for it to become a duplet structure or obtain stability, just like the noble gases. So we say that for hydrogen to do this, for it to become a duplet structure, which is this, it just needs one more electron. Now we'll be looking at the oxidation numbers of hydrogen. But before we talk about the oxidation number of hydrogen, we'll be looking at what oxidation number is. So we say that the oxidation number of an element is a number that is given to an element in a chemical combination which represents the number of electrons gained or lost by that atom or element. Here we have different oxidation number of different elements. For example, sodium, when combined with chlorine, in this reaction, sodium will give out 1 electron, to become a sodium ion, while chlorine will accept 1 electron from sodium atom to become a chlorine ion. So sodium will have something of this nature. Sodium would have sodium plus this, giving us the sodium ion. And we'll also have chlorine, giving us the chlorine ion. But here, the oxidation number of sodium would be what? +1, because it is giving out just 1 electron in this reaction. And because it is the one given, the sodium ion carries a positive charge. That is why we have this. But chlorine will carry a negative charge on it because it is receiving 1 electron from sodium. So we see that if we want to talk about oxidation number of sodium and chlorine, we would say that the oxidation number of sodium is +1 and the oxidation number of chlorine is -1, according to this definition. Remember, we said that it represents the number of electrons lost or gained by an atom of the element in a compound. Now, let's talk about the oxidation number of hydrogen. Hydrogen has 2 oxidation numbers. They are +1 and -1. Now, the oxidation number of hydrogen is +1 when it is combined with non-metals such as carbon, nitrogen, chlorine, fluorine, etc. We have examples as when hydrogen is combined with carbon, when it is combined with nitrogen, chlorine, or water. For example, let's use HCl, when hydrogen is combined with chlorine. In this reaction, hydrogen is the one giving out an electron to chlorine. So that is why the oxidation number of hydrogen in this reaction will be +1, while that of chlorine will be -1. So hydrogen carries a positive oxidation number of 1 when it is in reaction or in combination with non-metals. But when it is in combination with metals, it forms what we call metal hydrides, and it carries an oxidation number of -1. Take, for instance, sodium hydride. Sodium is reacting with hydrogen here, and of course, sodium is more electropositive, so sodium would actually give out an electron to hydrogen to become positively charged, while hydrogen in this reaction will be negatively charged. So these are the 2 instances where hydrogen either takes up a positive or a negative oxidation number. Now we'll be looking at the isotopes of hydrogen. Isotopy happens due to variance in atoms. It means that an atom may have the same number of protons but different number of neutrons. So hydrogen has 3 isotopes. They are protium, deuterium, and tritium. Looking at the image, the diagram here, protium has just 1 proton and 1 electron. There is no neutron. While in deuterium, deuterium has 1 neutron, 1 proton, and 1 electron. But in tritium, we have 2 neutrons, 1 proton, and 1 electron. So you see that the difference is in the number of neutrons these different isotopes possess. Deuterium and tritium have neutrons in them, while protium does not have a neutron. Now we'll quickly take a look at these three isotopes and really see their key features. For protium, we have established earlier that it consists of one proton and one electron. It doesn't contain a neutron. But out of the three isotopes of hydrogen, protium is the most abundant at 99.98%. It is most abundant in nature. But it does not occur in its pure form, but most times it is found bonded with itself as hydrogen molecule, or it is also found bonded with other elements. It is unreactive and the most stable hydrogen isotope because of this form in which it is found. In usage, it is mainly used as fuel in rockets and missiles. Deuterium. Deuterium is made up of one proton, one neutron, and one electron. After protium, deuterium is the second most abundant hydrogen isotope. It is equally non-reactive and stable in nature. It is known as a heavy hydrogen because of the possession of that neutron in the nucleus. In usage, it is used in heavy water-moderated fission reactors, usually as liquid water. Tritium. Tritium is composed of one proton, two neutrons, and one electron. Out of the three, it is unstable and highly reactive in nature, and it has a half-life of 12.32 years. It is used mainly in nuclear fission reactors and in neutron generators. Well, the isotopes of hydrogen show similar chemical properties. This is because they have the same atomic number. Atomic number simply means number of protons. So you see that they have the same or equal number of protons, which is 1. Okay? Most times, isotopy does not affect the chemical nature of elements. For example, the way protium will behave in a chemical reaction is the same way that deuterium and tritium would behave in a chemical reaction. But what isotopy does is that sometimes it affects the physical properties of elements. So these hydrogen isotopes which show a different physical property due to the different masses caused by the presence of neutrons. So deuterium will obviously weigh more than protium. Tritium will weigh more than deuterium. Then deuterium and tritium would weigh more than protium. So the difference is just in their physical makeup. Isotopy does not affect their chemical makeup. Now we'll be looking at the unique position of hydrogen, okay, in the periodic table. Now, when we look at the periodic table, hydrogen is the first element we see in the periodic table. And it is placed at the top of the alkali metals. These metals here are known as what? Alkali metals. We have lithium, we have sodium, potassium, rubidium, and the rest. Hydrogen is placed on top of them, although hydrogen is not an alkali metal. Now, these are some of the things that make hydrogen unique. Now, in behavior, hydrogen behaves like alkali metals, and it also behaves as halogens. How does this happen? Hydrogen behaves like alkali metals because of its ability to be able to lose its only electron to form a hydrogen ion. Remember when we gave instance with hydrogen chloride? Okay, we said that hydrogen in this reaction, hydrogen will give off its only electron to chlorine to form the hydrogen ion, while chlorine will accept one electron from hydrogen to form the chlorine ion. So, in this regard, hydrogen behaves as alkali metals because this is what alkali metals do. For example, if we take sodium, sodium is an alkali metal. If sodium is reacting with chlorine, it will also be the same thing. It will give out its one electron, okay, in its outermost shell to chlorine to form the sodium ion, okay? So hydrogen behaves like alkali metals in this regard when it forms positive ions. Then hydrogen behaves like halogens as well because it has the ability to gain an electron to form the hydride ion. For example, sodium hydride. Okay? Hydrogen can accept an electron from sodium to form the hydride ion. So, hydrogen is said to be unique because of its ability to lose its only electron to form the hydrogen ion and its ability to gain electron to form the hydride ion. We'll be looking at the resemblance of hydrogen to alkali metals and to halogens. Resemblance of hydrogen to alkali metals. 1. Hydrogen has only one electron in its valence shell, just as alkali metals. Lithium has just one electron in its valence shell, so does sodium, potassium, and other alkali metals. It shows a +1 valency. Of course, it gives out this one electron that it possesses in its valence shell to another atom for it to become a hydrogen ion, possessing a +1 valency. And that is also what happens to alkali metals. Hydrogen readily loses its electron to form a positive ion. It also readily combines with non-metals such as oxygen, fluorine, sulfur, and others, just as alkali metals. We're looking at how hydrogen resembles the halogens. Here on the periodic table, we have the halogens. Okay, we have fluorine, chlorine, bromine, iodine. Hydrogen resembles the halogens in that it is a non-metal, despite the fact that hydrogen is found on top of alkali metals. It is actually not a metal. It is a non-metal, just as the halogens. It is diatomic. Remember, we say that it does not occur on its own in nature, but most times it is found as a hydrogen molecule. And most halogens are also diatomic. Fluorine, chlorine. Okay, chlorine is written this way. Bromine and iodine. They are all diatomic, just as the hydrogen molecule. It shows a -1 valency, as it requires one electron to complete its valence shell. Remember that we say that for hydrogen to become a duplex structure, it needs one electron. When it does this, it becomes a hydride ion with a negative valency. Then hydrogen can form both ionic and covalent bonds. For example, in HCl, hydrogen forms an ionic bond here, while in methane, CH4, it forms a covalent bond. Now we'll be looking at the physical properties of hydrogen. Some of the physical properties of hydrogen are: hydrogen is a colorless, odorless, and tasteless gas, and it is highly inflammable. Another physical property is that hydrogen is the lightest known substance. In fact, it is 14.4 times less dense or lighter than air. Hydrogen also has a low boiling point at -253 degrees Celsius and a melting point of -259 degrees Celsius. Hydrogen is neutral to litmus, so it doesn't turn it red or blue. It is neutral to it. It is relatively insoluble in water, with only about 2 cm³ of hydrogen dissolving in 100 cm³ of water at standard temperature and pressure. Some chemical properties of hydrogen are that: 1, hydrogen forms the negative hydride ion by accepting one electron from any atom it combines with. So when hydrogen combines with an atom, for example, a metal atom, it will form the hydride ion. 2, hydrogen forms covalent bond with itself, as in when it bonds hydrogen to hydrogen, it forms covalent bonds. It can also form covalent bonds when it bonds with other elements such as fluorine, chlorine, oxygen. It does this by sharing its lone electron. Hydrogen is an electron donor, as it donates its lone electron to form the positive hydrogen ion. We saw that also when we made reference to hydrogen chloride, where hydrogen donates its electron to form the hydrogen ion. Now, this hydrogen ion can go into chemical combination with compounds. So it has the ability to enter into coordinate bonding, what we call coordinate bonding, with molecules having lone pair of electrons. For example, hydrogen ion, this hydrogen ion that we see here, can form what we call the hydronium ion, H3O, okay, with water. It can also form ammonium ion with ammonia. How does this happen? Okay, you can see here, we have the hydrogen ion and we have ammonia. Now, when ammonia is written out, okay, in the Lewis structure, we would have nitrogen with a pair of electrons that is not bonded to any atom at all. So what happens is that the hydrogen ion bonds here and forms what we call ammonium ion. So that is what we have here. The hydrogen ion can also bond with a water molecule, as we can see here. The water molecule with two lone pairs of electrons. Okay, so the hydrogen ion can easily bond on one of the pairs to form what we call hydronium ion. Still on chemical properties of hydrogen. During chemical combination, hydrogen acquires the duplet electronic configuration. For example, when it forms the hydrogen molecule with itself, or when it forms the hydronium ion with a compound of water. For example, just as we saw earlier, okay, the hydrogen ion can actually become a duplet structure when it combines with this water molecule, giving it 2 electrons. So it becomes stable. Another chemical property of hydrogen is that it bonds in air, forming water, although hydrogen does not support combustion. With this, we have wrapped up our lesson. Let's take a quick summary of all we treated today. We said that hydrogen is a chemical element with symbol H, and atomic number 1. We also say that the electronic configuration of hydrogen is 1s superscript 1. Then oxidation numbers of hydrogen are +1 and -1. Then we also mentioned the 3 isotopes of hydrogen, which are protium, deuterium, and tritium. Then we looked at the physical and chemical properties of hydrogen. A quick test. Now, which of the following hydrogen isotopes has 1 neutron in its nucleus? A, protium. B, deuterium. C, tritium. Okay. If your answer was B, then you answered correctly. Remember, we said that deuterium has 1 proton, 1 neutron, and 1 electron. Another question. Which of the following shows the resemblance of hydrogen to alkali metals? A, hydrogen shows a -1 valency. B, hydrogen accepts an electron from other atoms. C, hydrogen shows a +1 valency. Okay, if your answer was A or B, you're wrong. Our answer is C. Remember, we said that one of the resemblance of hydrogen to alkali metals is that it shows a +1 valency. With this, we have come to the end of our lesson. Thank you for staying with me. 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 For staying with me.